We're prepared today to start moving some charges and give you a little taste of electricity before we close, since we use it all the time in our world. Do you guys have any questions or concerns about the other electrostatic stuff before I begin? Friendly reminder then that this homework is still open. It's due Sunday, but it's not required. I made it so it's not required anymore. It'll be extra credit if you complete it. If you don't complete it, it won't harm you. It'll help you if you do. This material will be on the final, but the homework, again, extra credit. And it's due Sunday. You're welcome. We'll have one more class after this one on Monday, and I've planned a different type of review for the final. Hopefully you'll enjoy it. We obviously can't cover everything in one lecture, but I made a bunch of questions, and it'll at least prompt your mind and learn where you stand. Okay. The one thing in chapter 22 I haven't covered yet on electrostatics is capacitors. I've already leaked in some of the stuff with electric current in chapter 23, and we'll do more of that today. But the last little thing that I haven't quite got to in 22 are capacitors. Capacitors. They store charge. What a capacitor is, it really is nothing more than an insulator sandwich. This styrofoam is an insulator, meaning charges won't flow through it. It inhibits the flow of those electrons. Insulator. The metal are conductors. The electrons are loosely bound and they're free to move, and so they conduct electricity well. So two conductors separated by an insulator make a capacitor. This can store charge. We can build up charge on one side, and we can build up the opposite charge on the other side. And they can't get to each other. So they're attracted, right? Positive and negative. And so we store energy in a capacitor also. It's stored in the electric field between the two conductors. So a capacitor stores charge, it stores energy. The only way it could get from one side to the other is if you put this in a circuit. You connected this side to this side through like a wire. Then it could equalize. This right now is neutral, which means it has positives and negative charges. They're in balance. If you start separating the charges and putting some negatives on this side, positives on this side, it's still neutral overall. One side will be charged, and this side will be charged, but do you see that the capacitor in and of itself would be neutral? Because they're balanced. The same number of charges that get on one side will be on the other. Does that make sense? So that's all a capacitor is. It stores charge. So let's charge one up. Here's a big bad one. They're usually small in your little circuits, but you can't see those anyway. So here's a big one. These are connected to the two conductors inside. Now, the geometry, I should say, isn't always this simple. This works. But you can store more charge and energy if you can increase that surface area. If these were bigger, or if they were closer together, you can store more charge. And so one thing they can do is, it could be like two sheets of aluminum foil separated by wax paper. That way you could get them really close. Big, and you can roll it up, have lots of it. That could store a lot more charge than this could. So they do something like that in here. There's other ways. I'm going to connect each of those sides up to this power supply. I'm going to set it at 4,000 volts, and I'm going to turn it on. So this is doing work. The electrical energy is separating the charges. Remember we did that? If you had a positive and negative charge, it takes work to pull them apart against that electric field. And you can store that electrical potential energy on the two sides of the conductor. That's what we're doing right now. It's separating and charging it up. So I'll turn it off now, unplug it. And it'll hold that charge for weeks, months, unless you give it a path from one side to the other, which I'll do. I'll just short it out with this. You ready? Yeah, that's why I'm insulating myself from it. This one could do some harm. Want to do it again?
Why is wood not a conductor?
Well, this isn't wood, but wood can conduct or not. When we had our electroscope, remember, it actually did conduct. Not great, but it can. So it insulates you, but actually when you get up to high voltages, wood doesn't insulate you as well. Or if the wood is wet, the moisture in it can conduct. So sometimes it's a good insulator, sometimes it's not. This is actually called, I always forget the name. Phenolic. It's compressed and really good. So you can look it up. It's a good insulator. That's why I use it. Phenolic, PHYS. So this time, let's do it again. I'll make it a little dimmer so you can see the spark. I forgot to turn it on. It's all right, it only takes 10 seconds for this thing. So again, we're using this electrical energy to separate the charges. It's being stored as electrical potential energy between the plates of the capacitor. We'll turn it off, disconnect it. It's on its own. Do it this way so you can see better. And we'll let it flow from one conductor to the other, and that charge is released. Whammo! And it's converted, that energy is converted to heat, light, and sound. So energy is still conserved. Capacitors are just a nice way to store the energy. They're like batteries, but batteries get used up. It's chemical energy. They separated the charges, and then it comes out. But once you use up those chemicals, it's gone. Capacitors, these are some capacitors. So I'm going to connect them to the battery. So it's just like the power supply to this. These are charging up. We're using the energy of the batteries to separate the charges. You can discharge and recharge a capacitor indefinitely. Now it's connected to nothing. Now I'm going to connect the capacitors to this light bulb. And so now it drains the capacitors, creates light and heat, but now it's used up the capacitors, I assume by now, yeah. And they don't have enough energy. So it uses these up quickly, obviously. We didn't want to sit here and wait an hour anyway. So you can charge them back up, store the energy in the electric field. It's just like lifting something up. It's ready to do work now. It has the potential to do work. You push it off, and the gravitational field accelerates it and gains kinetic energy. Well, here, we turn it into something else. It's all capacitors do. They're very, very handy. All right. Questions about those? Yeah?
So where does the energy within the capacitors go after you still leave it? So you said about 3 weeks it'll die down. Is that because the electrons are trapped in stuff like the air molecules around it?
It needs a path to get there. This is a quick way. The air is pretty insulating, but not completely. Humidity in the air allows charges to leak off because they find a conductive path. And so it can do that slowly over time. A good capacitor, the older TVs, the cathode ray TVs, not the ones you guys are growing up with now, but service repairmen had to be very careful because they'd open up the back and they'd have these flyback capacitors. And they would hold charge for years. And if they touched in the wrong spot so that it did that, they got zapped. And a lot of people got harmed that way, so they had to be careful. This is a capacitor. It's a water bottle. Aluminum foil on the outside, conductor number 1. Water on the inside, conductor number 2. The plastic insulates and is separating the two. So I'm going to use that Van de Graaff from yesterday, or Wednesday. Charge this up. And now we've separated the charges and they're stored in here. And let's use this as a transition to talk about circuits. We want this charge to flow through us now. Now, I realize I just did this one, and that scares the bejeebies off of you. This one's safe. This one has high voltage, a lot of push, but the amount of charges it moves around is low. And so this is low energy. I'm not going to harm anybody. But we do need a circuit. This will only work if we have a circuit. So what I'd like is, we could all fit. If you came down here, or those you want to, and formed a circle and held pinkies with your neighbor. And the more people we have, the more resistance there is in the circuit. We're going to try to push that electric potential, that difference in voltage between the two sides of the conductors, sets up an electric field through us. That'll try to push the charges in us around. The more of us there are, the more resistance there is, and less charges will get pushed, and it won't feel as bad. So if you're worried, talk your friend into coming down. It's fun. No. Think about it. If I kill you, I'm going to get in lots of trouble. So join pinkies with your neighbor. No other takers? Really? Oh, come on. You don't have a pinky? What? Okay. Now, lessons about circuitry. Current can only flow if there's a path. If you guys let go, the electric field isn't established because it can't see that potential difference. The difference in voltage. Voltage is electric potential. They're the same thing. It can't see it, and if it can't see it, they don't get pushed. So we can't let go. Another thing is we're a series circuit. We're all connected in series. It has to get through you before it can get to you, that field. And so we want it to stay through us. Nobody's leaking, touching, leaning against this. We also need a switch. Who would like to be the switch? Me. Okay, you guys hook up, and I'll come in here. I'm going to hold the outside of the bottle. I'm going to hold your pinky. Oh. We're the break, so it's not connected. The only way charge can get from the outside foil to the water is through us. She's going to touch the bolt on the top when she's ready, and we'll see what happens. You guys ready? You sure? Okay.
Okay. Going back.
Yep.
Shoot!
I didn't say it wouldn't scare you. I just said it was. Thank you very much. See, that was fun. Let's make sure we got it all out. There we go. It surprises you. It quote unquote shocks you more than an electrical shock. Again, this is a high voltage fairly much. Pushes a lot of charge, but the charges that are moving aren't that many.
What does it run through in your body?
It goes through our arm, across and out the other, usually on the surface of the skin. Yeah, this is very, very little is going through your heart. And the amount of current, I've calculated this, is really, really small. Remember, current is what kills? Current is the flow of charge, how fast it's flowing. I'm going to write it out on the board later, but current is the charge over time. How much charge passes by or flows in a certain amount of time? That's current. Voltage is electric potential that sets up that electric field. Remember, if you have charges in an electric field, they're going to accelerate, depending on whether they're positive or negative, so they get moving. Where was the source of our charges for that circuit? I know you have a question, Eddie. Where's the source of the charges in that circuit? Yeah, a lot of people think the bottle. That separated the charges on it, but it's not right to think that all the charges got shoved into here. We just separated charges, put the negatives on one side and the positives on the other. This was still neutral as a whole. What it did is it set up an electric field through us as soon as you connected the switch, and all the charges in us felt it and started moving. So we're the source of the charge.
And did you feel it?
Oh, we all felt it. Yes, Eddie.
All we found was when you charge this capacitor, you had a positive and negative.
Yes, positive and negative. This would be positive and negative too. The outside and the inside. One would be positive, one would be negative.
Right, but you connect the positive and the negative charge that way. Why don't you only connect one cable to the...
Oh, you didn't see it. I did actually connect both. I needed a circuit for the charges to flow. So I had this to one. I was holding this, and when I touched the switch, after I turned it on, I actually touched a grounding bar down here. But it can go through me too. I'm grounded. This is grounded, and so it's like a big circuit through the earth. So yeah, I did actually. Good observation. That I have to remember how this charges up. Let's say this gets charged negatively, then yes, they would get on the inside. And the positive, well, it's discharged now. Although I had a friend, long story short, we did this a lot in Colorado, and he swore it was discharged. Somebody was debating with him, and he's like, "Oh, I'll prove it to you." And he goes like this. Yeah, it wasn't discharged. And he got all of it through him. He said his neck muscles were sore for weeks. So we're learning lots with this. Some other observations. Were you afraid to be the switch?
No.
Oh, you're brave, because most people are. They think touching it, it's going to hurt more. Well, you guys all jumped about the same amount. You all felt the same thing. Something I want you to know also is in a series circuit like that, the current is the same for everybody. It has to be, because the electric field had to get through me before it could get through you, and so they all started moving the same. The current in a series circuit, wink, wink, is the same everywhere. Yes?
Well, I felt like this rock was the same with an electric dog collar. A couple of us have felt like what that's like, and so, but how is that
You have, huh?
How is that possible if, like, is the current smaller than that bottle? Because I feel like if one dog, like, felt it, it would totally just...
The current in a dog collar, I haven't studied the numbers in it, but it's got to be a safe amount. It's a shock kind of similar to what you felt. I think if I had a collar on and felt what we just felt, I would stop what I'm doing too. So that was sufficient. So if it's just one dog, I would think, yes, they would use less energy to have the same effect with just one, which is the other thing. The more people we add again, the more resistance there would be, and less current would flow through the circuit. We would all feel less current, because in a series circuit, we all feel the same current. It's the same. If you hook up a light bulb and a microwave and a motor in series, they all get the same current, because it has to get through one before it can get to the other.
So would that leave, if you added more resistance to the circuit, would that leave more charge remaining?
Would it leave more charge in here? No. Basically, more resistance that the charges are trying to move through, and so less current would flow or go through each one, but it takes more energy to do that. This is still providing the same push, the same electric field. It's just we wouldn't feel individually as much. It's like 4 light bulbs, which I'm going to do. They still get it. They get less energy each, but there's more of them. That helps. So yeah, you still can drain your power source, absolutely. I see there was another observation. Oh, so since we're the source of the charge, all the charges in us started moving at the same time. A lot of people think electricity takes time to flow. It's quick, they think. They think you flip on the switch, and the electrons are going, and they all light up. But the one closest to the switch gets lit up first, and then, no. As soon as you close the switch, everybody feels the electric field at the same time, and all the charges start moving at the same time. You feel the same thing. You guys all felt the same amount. And the actual charges themselves are moving really slowly, actually. The electric field is like a wave, and that's fast. But the charges themselves are moving maybe a centimeter a second, like a snail's pace. Why? Because they run into other particles. If it was all by itself in space, right, it could, but it runs into something. And so it's kind of going like this. And maybe on average, it moves about a centimeter a second with direct current. Direct current is a battery, like these batteries. This pushes, the electric field's always in one direction, so the current flows in one direction only. And that's what, the charges will just slowly drift. If you've ever heard of drift velocity, that's what an electron's doing, slowly kind of drifting through. DC, direct current. Alternating current is what comes out of the wall. The electric field changes. In the United States, it's 60 hertz. You know what that is now. That means it changes direction 60 times every second. Go that way, go that way. And so the net effect of an electron, it doesn't go anywhere. It's moving because of the electric field, but it runs into things. But then it's accelerated the other way and runs into those and then the other way. And so those charges don't really go anywhere. So don't think of electricity as electrons whizzing around. So you actually pay the power company for the push, the power. The energy is what you're paying the power company for. You're not paying for the current. You already have it. The charges are already in your wire. You just need something to cause them to start moving, try to accelerate. And that's where we tap into that and use that as the energy. Let's show you alternating current, AC. That's what comes out here and changes direction. This is a little LED. And I'm going to turn it on. You can see the color. It's a red and green LED. Red and green light combined to make? Yellow. So it probably looks yellowish to some of you. Let's turn the lights off because it's cooler with the lights off. What's that? Well, let's see. I bet that looks red to you. What's that look? Let me turn the lights off. It'll be more conspicuous. I don't know. Is it more yellow now? More red? Well, I'll show you. It's really red and green. Ready? It's like that color mixing ball. And they're not on at the same time like our color mixing ball. When the current is flowing in one direction, or I should say the electric field is in one direction, let's say the red light comes on when it's positive. If it pushes it in the opposite direction, negative, the green LED's lit. You can see they're not lit at the same time. And so it's alternating and changing directions. See the black spot in between the red and the green? Mm-hmm. That's where the power company's gypping you, and you're getting no power at all. Who's annoyed? Well, let me draw a graph on the board and explain that. It's back to our sine wave. Here it alternates. The voltage, the push, increases in one direction, maxes, comes back down, and then goes the other way. And then pushes this way, and then pushes this way. The electric field changes. It's positive, negative, positive, negative. That's why it changes directions. Right here, every time it crosses the 0 point, the equilibrium position, it's not pushing any. That was the black spots. That's just when it's changing direction. So you're not really getting gypped. It's just switched from being one direction to the other direction. So, when the power is going this way, you might see the red LED, and then the green, and then the red, and then the green. This is alternating current. You might find it interesting, too, that 120 volts comes out of the wall. It's 120 volts AC. That's kind of like an average. It's something called root mean squared that I'm not going to hold you to, but some of you might have heard of it, root mean squared. This actually maxes at about 170 and negative 170 when it's oscillating. What's the average value of the sine wave? On average, what's the value? Nope. 0. Half the time is positive, the other half's negative. So the average is 0. So we can't use the average 0 wouldn't help us calculate anything. So they came up with this value called the root mean squared, and it's kind of like on average, something we can use that's consistent. And that's the 120. It's not the real average, because the real average is 0. But we say it's 120 volts. Well, it's always changing. Well, it's this. No, now it's this. Oh, wait. Is it? Well, we got to give it a number. So that's what we do. So just because it's a fixed number doesn't mean it's not changing. It always is, 60 times a second.
But for example, they say that when that oscillates, that's what spoils the computer.
Yes, that change, that alternating, is hard on a lot of electronics, yes. Especially it can fry some computers if it's the wrong frequency. Some things are built to work at 60 hertz. If it's on something else. That's why if you travel and you plug in, you got the wrong voltage sometimes. Different countries use different voltages, but they also use different frequencies. And that can fry your components, depending on how they're built.
We have, for example, lights for photography that the Germans, they have two switches for that. One is for 120 and the other is for 240.
There you go, the different voltage, yeah. Because a different voltage, if you doubled the voltage, how do you think, you don't change the circuit. The circuit has the same amount of resistance in it. If you double the voltage, the push, the electric field, how do you think that'll affect the charges through it? It'll double. Well, it'll double, yeah. Since we're on that, do this, see if I come back to that's called Ohm's Law. And I wanted to cover that today anyway. Ohm's Law. There's one main relationship with electricity, and it's the amount of current that flows in a circuit. Voltage over resistance. That's pretty much it. It's how they're related. And you already know this, but let me backtrack. Current, now that I'm writing it up here. I use an I. Current is the flow rate of charge. So you take that charge, how much charge passes in a certain amount of time. It's just the rate charge moves by. So that's all current is. Voltage, we already did. That's the electric potential. You remember? Voltage is energy per charge. That electropotential energy. Energy per charge. Instead of having to deal with them individually. And resistance, I usually don't have to explain. That's, what it's trying to go through. If you had something really thick like this, maybe a really big wire, compared to an itty-bitty skinny wire, which one do you think it's harder to get charges to flow through? I like using water as an analogy through pipes. It's very similar. Is it easier to get water through something narrow or something wide? Wide. It's kind of how it works with resistors. You can think of them that way. This would have less resistance. And this would have more resistance. Physically, that works. Bigger wire, it's like it has different paths to get through, so it's easier. But if you have a narrow one, it all has to get channeled through there, and that'll provide more resistance. And we already discussed, if you add a second one of these and attached it to it, and a third, and a fourth, and a fifth, that adds more resistance because it's like a longer wire, right? Longer wires would provide more resistance because you got more to get through. And that'd be true for whether it's wide or skinny. So maybe that'll help you with resistance. Size can matter, but also the length, how much you're trying to get through. It's all about that path the charge is trying to flow through. If it's got a lot more to go through, more resistance. If there's different paths it can take, more current can flow because it's easier. Ooh, yeah, I can go here. Oh, that one's blocked, I'll go here. It's harder to go this way, well, I'll go this way. And that's how it works, essentially. So that's how they got this relationship. More current flows if there's a higher electric potential. You push harder, you get more to flow. So they're directly proportional. And if you have more resistance, it's inversely proportional. Less current will flow. So that just helps us remember that relationship. Let's see if there's anything important I left out here. Oh, I didn't tell you the unit for current. Volts. Voltage is in volts. V. Resistance is in ohms. And it's a symbol omega. You ever see that? Current is in amps. It's actually ampere. You've heard amps and A. So that you're familiar with those. Heard volts, an amp meter. An amp meter, it measures current. What'd you say? Yeah, it's a guy's last name that it was named after, Ampere. We often short it to amps, or just an A. Ohms is represented by omega, and that's the amount of resistance you're seeing. That's Ohm's law. And that defines pretty much all electricity. They obviously can get more complicated, but that's still true, the relationship. You throw in funky things like capacitors and inductors and all these other things, and they have a resistance. And you have to add that into this, but it's still resistance. It's impedance, if you've ever heard that term. Remember, the only time current flows, the only time you get this flow of charge, have a current, is if there's a difference in voltage to establish that electric field. So again, you could touch a 1,000,000 volt high wire. Birds sit on high wires, right? Yes, I'm artistic. Well, it goes through a little bit of wire there that has resistance. But it's really close. It's a really short wire, so it doesn't have much resistance. So when current tries to flow through that resistor, it doesn't use up much energy. The voltage doesn't change much from one foot to the other. Can you see that? As you go through resistance, that's when this current uses up some of that energy that's being pushed. But if the resistance is small enough, this spot and this spot essentially have the same voltage. There's very little difference. And so not much current gets forced through the bird, and it survives.
And that's why it kind of
That's why they can sit on the wires. If we were to do that, we just increase the distance from like here over to here, right? Our foot. That's a lot more resistance. And so there's a bigger difference between over there and over here. And that can cause current to flow through us and electrocute us. And if we were even farther, Or say we grab a hold of this and touch the ground. Now you have the high voltage here and the low voltage there. Big, huge difference. And you'll definitely probably die. Because that'll push a lot of charges. Some will go through your heart. And no, it's just Ohm's law. There's very little resistance between their 2 feet. You will only get shocked if there's a difference in that electric potential to cause the charges that are already in you to start moving through that electric field. That's all electricity is. Yeah, Patricia?
If you put your feet together.
You're safer. Yeah, if your feet were together, you're more likely to survive. Yes, that's a good point. Emergency preparedness. Okay, you're out in a big field. There's no ditch to lie in. You can't hide out in a car where it'll shield you from the electric field from a lightning strike. You don't want to stand up because you're higher. You're closer to it, right? You've just decreased it. So you want to lay down in a field. But it's actually safer, instead of laying down and spreading yourself across the wire, the ground, it's less likely the lightning will strike you, but it could strike a tree next to you or ground over there, and it'll flow through the ground. So now the ground is a wire that you're sitting on. If you lie down, there's a bigger difference in electric potential from your feet to your head, and more current could flow. So they actually suggest that you put your feet together, squat down. This way you're lower, you're less likely to get struck. And if it does strike around you, it'll just have this short distance. Less current is likely to flow through you, and you're more likely to survive, be less harmed.
As far as the birds are concerned, situation like the birds, I've also heard that their feet insulated. Are they?
Some birds, their feet are different. Yeah, if you're insulated more, that would help. The thing is, at some point, what might insulate you from this, if you have enough energy, it might be able to break this down. Example is air. Air is usually insulating. But if you get a big enough potential difference between the clouds and the ground, it breaks down the air and it becomes conductive. So if you have enough energy, any insulator could break down. But yeah, in theory, if you wore big rubber boots, you could be insulated more. But these high voltage wires can probably break that down. You might be safe with this current, but maybe not that current. So insulators it depends on what you're trying to shove through in the first place.
Just one more question about that. So if you have your feet together and you're lower, then can you balance yourself with your hands, or does that put more?
That would do more, but if you needed to, then just have them close to your feet,
So that would minimize.
Yeah, that way it's still a short distance, but you don't have to wobble all the time. But yeah, most people would want to, there we go. But now you're in a little more danger. See, life lessons. Let's do a series circuit. So I have a car battery, DC, direct current. This is going to push it in one direction. I'm going to send it through a resistor. And to demonstrate that, because you've probably never seen a resistor like that before, here's one. Whoops, power's on this side. Let's get power to the table. Here's my power supply. I turn it on, light comes on. It's in series. It comes from here, goes into here. I don't know if you can see this very well, but it goes along this top rod into this, connects to the coils of wire, and then makes it to the other side. So this amount of wire is creating the resistance. Then it comes to the bulb and back. This is a series circuit. It only has one path it can take. Now, if I change how much resistance it goes through, let's force it to go through more. I'm going to move this that way. So it'll have to go through more of this. What do you think will happen to the bulb? It'll go dimmer? Doo-doo-doo. Because we've increased the resistance. We can write Ohm's Law this way. The voltage across the bulb is based on the current through it and its resistance, or the whole circuit. And if we've increased the resistance, the current goes down. We're not having a biggest push across the bulb, and it gets dimmer. If we decrease the resistance, there we go. Something just shocked me right there. But all these bare open things. There's a little tingle. I'm fine. So that's a resistor. Hold down here. So when you're dimming your switch, your lights, it's usually just something like that. You're changing the resistance. Thus, you're just changing how much current and energy gets to the individual bulbs. Brighter. No, brighter. Dimmer. So let's do that over here. Oh, I looked at it. Now I can't see. So this limits the amount of current that can go into these bulbs so that I don't blow them. So here's one in big series loop here. It lights up. If I disconnect, no electric field. Let's wrap that up. Let's connect a second one in series with it. It has to go through both of these now, right? What do you think will happen?
They are gonna light.
They're going to light. Any difference from this to having to go through two of them? They're dimmer. There's twice the resistance. Let's add a third one. So in a series circuit, again, the current is the same through all of those. It has to be because there's only one path. But another tidbit, they're sharing the voltage. This battery is 12 volts. That's the electric potential from this side to this side. That's the energy per charge. As those charges get moved through the filaments, they use up some of that energy. They have to share it. So if this is 12 volts, and there's 3 bulbs, 3 resistors, how many volts do you think each one uses up? How much energy per charge is used up going through each bulb? 12 volts total, 12 across here, they have to share it, and there's 3 of them. 12 divided by 3. They split it up 3 ways, so they each use up 4 volts. There's 4 volts across each bulb. They share the voltage. This is what I want you to write down. In a series circuit, you have to share the voltage. But they all get the same current in a series circuit. And we'll do parallel next.
Does some of the voltage get eaten up by the resistance going through the cables?
Very good. There is resistance through the cables. It's a lot less because it's just a simple conductor and they're not very long, relatively speaking. But yes, this and each wire do have resistance. The resistance of the light bulbs is just a lot more, so I'm just keeping it simple. But you do have to account for that if you want to be totally accurate, yes. But they're all in series.
So what's that phrase in a series current?
So in a series circuit, the current has to be the same through each component. Does that make sense? Why? Because there's only one path. It's like water through a pipe. The same amount of water is going to get through the pipe. It might be wide here, it might be narrow here, but it's going to be the same amount of charge in the same amount of time. But they have to share the voltage. Let's do parallel. It might make it even put this together more. So let's go back to 1. Now I'm going to connect the second one. Basically, the current gets to here, and with this minimal resistance to this point, it's like we have 12 volts here, and we have 0 volts here. Those 3 bulbs used it up. They have to share it. Now, I'm going to give it a different path. It can go this way, or it can go this way. See how the current splits? So in a parallel circuit, the current is shared. Some of it goes this way, some of it goes this way. So these two, I don't know what the current is. Let's say it was 1 amp, 1 ampere of current. Then a half an amp goes this way and a half an amp goes this way because it can split. So in a parallel, the current is shared. The voltage is the same. So they're kind of opposites. Do you see how the voltage is the same? This bulb sees 12 volts difference from here to here, correct? Well, so does this bulb from here to here. From here to here, it's like it's at the same potential. We haven't lost much energy going through the rod because there's not much resistance there. It's same over here. So it's like this whole side's one potential and this whole side's the other. So they both get 12 volts. So they they have the same voltage in parallel. You add a third one. And notice these are a lot brighter too, don't you? Because they both fill the 12 volts. Where in series, they had to share it, that push, and you didn't push as many charges around. Third one. See, they're all equally bright. But now we've split the current up 3 ways. What do you think would happen if this had a lot more resistance than the other 2 bulbs? It would be dimmer because less current would flow through here because it'd be harder. And these would have more. It's still split, it just might not be evenly. Depends on their resistances. These bulbs are the same, so they look the same. But one interesting thing, well, to make that more clear, if one bulb goes out when things are hooked up in parallel, the others don't go out, do they? That's convenient. Where in series, if I undid one, I broke the path. They would all go out.
In this case, the paths are the rope.
They are the ropes, the paths, yeah. So your Christmas lights, when one light goes out, do they all go out? Depends on your string. If they all go out, they're in series. If they don't go out, they're in parallel. They make different ones. Sometimes they're in sections. This section's in series, but it's in parallel with this section. So if this bulb goes out, this whole section goes out because they're in series, but not over here, which makes it nice. Now, to maintain this brightness, more energy is being used here in parallel. Energy is conserved. When you hook these bulbs up in parallel, there's actually less resistance. This sees less resistance because there's more paths, right? It's like a bigger, wider wire cable. And since there's less resistance, this will push more current out. There's more current flowing out of the battery now when they're in parallel than when they're hooked up in series. Because in series, it sees more resistance, and so it can't push as much. So one disadvantage of hooking things up in parallel is it's going to cost you more money. You need more energy to push more current out, to keep them just as bright, or when one goes out, the others can still be lit. So there, see, it's conserved in electricity as well. Any questions? I think I'm done.
How does whatever's in the battery, how does it go through the current and make light?
Whatever's in the battery. There's different chemicals. Remember how when we separated different objects, charges separate? Hand-waving short answer is chemically, electrons will want to go towards one element compared to the other. And if you can separate those two, it's like they stay there like on a capacitor, and then they try to go through the electrolyte. Once you hook it up in a circuit, it gives it a path, and they'll flow from one element to another, different chemical to a different chemical, until that chemical is used up. So the energy is stored chemically in those chemicals and allowed to flow when you hook it up. Does that help? I did forget one thing. Just those of you looking at your homework, but you can look in your book. It's not hard, but just so you know what I'm talking about. And 30 seconds, as soon as I find the chalk. Here it is. Power. I'm sorry. Power. Do you remember from before? That's energy per time. It's how fast you're using up energy. We already discussed it though. Energy has to stay conserved. So if you increase the voltage, the current goes down and vice versa. But if you want to calculate the power, because most of you see that, a 100-watt light bulb. Remember, watts is power. That's telling you how much energy is going to get used up per time. Anyway, this is the relationship to calculate power with electricity. That's all there is to it. Because I think one of the homework questions asked you about power, so at least now you won't be clueless. But it's in your book. Thank you.